Hey there, grade 6. New video for you guys today. We're going to keep going with our patterns in algebra unit. And this time we're going to look at something called dependent and independent variables. And so the goal for the end of this lesson and the practice in the workbook is that you can learn about dependent and independent variables. And then what we're going to spend sort of the bulk of our time doing is interpret something called linear graphs. And so here is where we're going to start. We're going to start by looking at starting at the interpreting linear graphs. And so what it says here is that this graph represents the cost of parking a car in a parking lot. So then the questions are, let's start doing some interpreting. So here's the first question. How much would you pay for entering the parking lot even before you park your car there? And if we head over right here at 0 hours, it's going to cost us $3 just to get into the lot. Okay, second question then. So how much does it cost to park for 1 hour? Well, it's that $3 plus an extra $2. And so it would cost $5. And then to park there for 2 hours would cost $7. To park there for 3 hours would cost $9. But then notice that flat fee, or that, not a flat fee, sorry, that fee doesn't change. So once you've been there for 3 hours, that is as much as you are going to pay. In other words, the data is not, or sorry, the graph isn't going to change if you park there for 3 hours, 4 hours, 5 hours, 6 hours, and so on and so forth, right? So the hourly rate for the first 3 hours, the hourly charge for the first 3 hours changes. No, it's $2 an hour. But so what we would say is it's to figure out the fee for this, it's $3 to get into the lot, and then $2 for each additional hour, up to 3 hours, or for a maximum of 3 hours, or $9, right? So to think about it in a mathematical way, if you park for less than 3 hours, you would multiply the time, which is down on the x-axis, multiply the time by 2, and then add 3. And then if you park for 3 or more hours, the price is just $9. Okay, now moving on, we're going to look at a different problem. And so it says that a nearby parking lot charges just $2 an hour. So then if we think about the mathematical rule for the cost of parking there, right, you would say you multiply the number of hours by 2. So then you can plot the graph. Okay, and so I'm just going to do my little switch here and get a nice thin line going because I appreciate a thin line. Make sure that's a thin line. All right, so it's $2 an hour, right? So after 1 hour, it is $2. After 2 hours, it's $4. After 3 hours, it's $6. After 4 hours, it's $8. After 5 hours, it's $10. And we've lost sort of room on here, but it would keep going up. So what we have done is we've plotted the graph for the second rule. So which graph do you think would it be cheaper to park for 2 hours? So if we go back to the previous one, 2 hours here costs $7, and then 2 hours here costs only $4, right? What about for 5 hours? Well, then the first one gets cheaper, right? Because there's that flat fee. Once you hit 3 hours, it just stays $9. Whereas this one, if you park for 5 hours, it's $10 because it's $2 an hour, right? And so you could plot this or graph this out on like a table, right? Here are the two graphs. So for this one shows us for 2 hours, and this one shows us for when we get up to 5 hours, etc. How that stuff changes. Now what we're going to do is start looking at something called dependent and independent variables. So what we can do to start is writing the equation for the second parking lot. And so over here it says use the variable c for cost and t for time. So change the color over for a quick sec, keep it thin. And so the cost is going to equal 2 times the number of hours, or 2t. Okay, so that is going to be our equation. And then so the question down here says, what variable in this equation is the input? And that's maybe a bit of a difficult question, but let's try and make a bit more sense, right? So we have time and then cost. So for 1 hour, it's $2. For 2 hours, it's $4. 3 hours is $6. 4 hours is $8, etc. So the stuff on the left here, we're going to say that this is the input. Another way to look at it is that the stuff that's along the horizontal axis is the input. Oftentimes, time is the input. It's a constant change. It changes by 1. The stuff that's along the y-axis over here, that's often the output, right? So that's the stuff that can change depending on what you have to do to the input. In other words, what we're doing here is we're multiplying the time by 2, right? So every time it's like 1 times 2 gives us 2, 2 times 2 gives us 4, 3 times 2 gives us 6, 4 times 2 gives us 8. So this is going to change, right? Because if what we do to the input follows a different rule, then the output is going to be different. Okay, so getting back to this example with the parking lot, you can park in the parking lot for any number of hours you want, but the cost depends on the duration of the park time. So C changes depending on T, okay, and I'm talking about the variables there, depending on T, and because of this, in the equation C equals T 2T, we call T, I'm just going to change the thickness again, sorry. We call T the independent variable, and then we would call C here the dependent variable. Okay, and so again, the point I want to highlight here, look along the horizontal or the x-axis for your input or your independent variable, and then look along the y-axis or the vertical axis for your dependent variable, the thing that can change. Okay, so this stuff I've already talked about, this stuff I already showed you, so I'm going to move on over here. Now, here's a bit of a long question. A boat leaves port at 9 a.m. and travels at a steady speed. Okay, sometime later, a man jumps into the water and starts swimming in the same direction as the boat. The graph shows the motion of the boat and the man over time. So we're going to use the graph to answer the questions on slide 8. First of all, how many minutes passed between the time the boat left port and the time the man jumped into the water? And so if we look down here, if we go over to 15, right, this is the point where the man jumped in the water and started swimming. Before that, this horizontal line would mean that he's just on shore. Okay. So then the next question is, how far from port was the man at 9:15? So when he jumped in the water, so now this takes a bit more interpretation, but this point here represents 9 o'clock because that's when the boat leaves. So now this is 9:15. This is when the man jumped in the water. He was 3 kilometers from port. The next question says, when did the boat overtake the man? So we look at where the two lines intersect. Okay, and so that's 60 minutes after the boat left, and so that represents 10 o'clock, 10 a.m. Okay, and then the next question is, how far can the boat travel in 1 hour? Well, it traveled 6 kilometers, right? If we follow this steady line, it travels 6 kilometers an hour at that speed, okay? And then it said, how long does it take for the man to swim 1 kilometer? So to get from, say, 3 to 4, right, it goes over 1 and up 1, which represents a change of 15 minutes. Okay, so again, we're looking at the graph and we're trying to interpret the data. There's a couple more questions. F says, how far did the man swim before being taken aboard? Okay, so he swam. He started at 3 and swam to 6. So that means that he swam 3 kilometers. Okay, so he jumps in 3 kilometers from port and swims 3 more kilometers. Part 2 of that question says, how can you see from the graph when the man was picked up by the boat? Well, as we said, that is where the 2 lines intersect over here. That's where the man got picked up by the boat. Then the question is, did the boat continue traveling when it met the man, or did it stay at the same place for some time? Well, what we can see here is that the line flattens out. It turns into a horizontal line, which means that the boat stayed in place for about 15 minutes so that it could pick up the man. And then it carried on its journey at 10:15. The last question there says, the boat docked at another port 9 kilometers from the starting point. At what time did this happen? And so that is now 105 minutes. Okay, so that's 9 o'clock, that's 10 o'clock, okay, that's 10:30, and that's 10:45. And so the boat docked at 10:45 a.m. at another port. And so again, we've learned about independent variables. We learned about dependent variables. That has to do with whether or not the number is along the x-axis or the y-axis. We learned about interpreting graphs and looking at the data. And so what you can do with all that stuff is you can go to page 91 and 92, work through the questions. You will more than likely need an extra sheet of paper because number 5, you really don't have enough room to write down that stuff. So work on that stuff and then make sure you mark it as done in the classroom.